All right, so in part A, we have to show that a converging sequence of complex numbers has a unique limit. Okay, so we're going to go ahead and let z sub n be a complex sequence where n is a natural number, right? So what does that mean? That means that we have the sequence starting at maybe z1, z2, z3, and so on and so forth. And we want to try to prove that this sequence converges. If this sequence converges to some limit z, then z is unique. Okay, so how are we going to do that? Well, what we're essentially going to do is, so this is kind of the outline. The outline is going to be show that if z sub n converges to z and z sub n converges to maybe another limit w, that's going to imply that z equals w. Okay, but we have to be kind of careful about how we show this because we want to be as rigorous as possible. And so in reality, in order to show that z is equal to w, we have to show that for any, we'll call it epsilon positive, that's arbitrary, we have that the distance between z and w is less than epsilon. In other words, I can make the difference between z and w as small as I possibly want it. And since epsilon, whenever I say epsilon is bigger than 0, we really think of that as being such an incredibly small number, as small as you could possibly make it. That's actually the idea behind a limit. Okay? So that's what we're going to show. So let's go ahead and do that. And so let's go ahead and assume, or I guess we should let epsilon be positive, and we're going to let that be arbitrary. Okay, and then since the sequence z sub n converges to z, and z sub n also converges to maybe w, that means that for every epsilon positive, there's going to exist a natural number n such that for little n in the sequence bigger than or equal to capital N, or in other words, this is some sort of threshold, such that terms beyond the capital nth term in the sequence, we get that the difference between z sub n and the limit z is less than epsilon, and the difference between z sub n and w is less than epsilon. But since this really doesn't matter, I mean, I could make this anything as long as it's arbitrary. I'm going to go ahead and actually let it be epsilon over 2. You're going to see that the proof's going to work out a little bit nicer. Okay? So again, what does that mean? Well, you can imagine, again, this is all working in two-dimensional space, right? And so z sub n is going to be some sequence of complex numbers. Maybe it converges to 0, 0. It can converge anywhere, but maybe it does something like this, right? And so every single term of the sequence is just going to get closer and closer, right? This magnitude, if I take the magnitude between that magnitude, and that magnitude, and that magnitude, they're getting closer and closer. If I take the distance between my supposed limit and each of these points, they're eventually going to get within a circle of radius epsilon, where I get to choose epsilon to be whatever I want. That's essentially what I'm saying. Okay, and so by that logic, what we're going to do is we're going to take this inequality, we're going to take the absolute value of z minus w, and we're going to kind of manipulate it a little bit. Okay, so the trick with this, and of course this is the same as the proof with real numbers, is note that the absolute value between z and w, right, the difference between them, we want to show that that's less than epsilon for any epsilon which is already arbitrary. And so I'm going to insert a z sub n. And of course, if I insert it by subtracting it from z, I also have to add it so that this is 0 and I didn't change the term. Okay, so we do indeed get equality. Okay, and now since I proved the triangle inequality, I have two, right? I have two complex numbers. I have z minus zn and zn minus w. Those are two complex numbers, so by the triangle inequality, that's going to be less than or equal to the modulus of z minus zn plus the modulus of zn minus w. Okay, and the next thing that I can technically do is I can take these two terms and I can flip the order of them, right? With subtraction, we know that, a minus b can be written as b minus a at the cost of a negative sign. And since we're taking the modulus in both cases, the modulus of this is really just going to equal the modulus of the positive version because the negative one factors out, okay? And so this is essentially going to be equal to, and then we'll say, Zn minus Z plus Zn minus W. And you'll notice that for capital N being that threshold we talked about earlier, as long as little n exceeds that threshold, what we have is that both of these terms are going to be less than or equal to epsilon over 2. Okay, and that's going to equal epsilon. So we've showed that distance between z and w can be made as small as I wanted to. And that kind of concludes the proof for part A. Part B says, prove that a sequence of complex numbers converges if and only if it is a Cauchy sequence. So there's a very similar theorem for the real numbers, and the idea is as follows. So if you have a convergent sequence, that's going to imply that the sequence is what's called Cauchy. And I'll define Cauchy in a second, but it's important to note that this direction holds for any metric space. So as long as you can show something as a metric space, that direction automatically holds. Okay, however, it is not always true in all metric spaces that being Cauchy implies that you're convergent. In other words, if you have a Cauchy sequence that lives inside a metric space, it's not always true that that converges. Okay, and so if that holds, then you have what's called a complete metric space. Okay, and it turns out that the real numbers and the complex numbers are both examples of complete metric spaces. Now, we are going to take for granted the fact that the real numbers are complete, and we're essentially going to show the complex numbers are also complete. So why does that hold? Well, I think intuitively it kind of makes sense, right? If I said the complex numbers are really just the same as r cross r, right? Z sub n is really just, I could write that as a sequence of real numbers, real components, and a sequence of imaginary components. And individually, if I say that Z sub n converges, that means that x sub n and y sub n both have to converge. If one of them diverges, then this has to diverge. Okay, so I think intuitively it makes a lot of sense, but let's kind of show this a bit more rigorously. But before that, I should probably define what a Cauchy sequence is. So I should start by saying maybe let Zn be a complex sequence. Sequence of complex numbers. Then we say that Z sub n, and I'm going to not always write that, obviously n is a natural number, but we say that that is Cauchy. We say that it's Cauchy if for every epsilon arbitrary, there exists a natural number, some threshold capital N, such that for two terms in the sequence, for any two terms n and m that both exceed the threshold, we have the difference between those specific terms is less than epsilon. So this is technically different from the definition of convergence. Why? Because the definition of convergence requires you to know in advance what the sequence is converging to. And with Cauchy sequences, you don't need to know that in order to show that it converges. All you need to pick is two arbitrary elements of the sequence that are beyond some threshold and show that, you know, as essentially as basically as n goes to infinity, n and m go to infinity, the difference between these terms gets smaller and smaller. Okay, so just to give you a quick little picture before we actually start this proof. So I'll try my best here. So again, I'll maybe use the example of we know it converges to 0, 0, but we don't need to know that. And so our sequence might look something like this, where it kind of does this, but it like gradually gets smaller and smaller and eventually converges inwards like that. So basically what we're saying is for any epsilon, okay, so for any kind of epsilon ball that I can draw around here, you can essentially find a threshold such that for any two terms beyond that threshold, they are going to be within epsilon, right? So you can connect any two of those, and that's going to be smaller than the radius of that circle. And so you can kind of think about how that doesn't necessarily imply that something is convergent. The definitions are pretty different, but let's go ahead and prove that the complex numbers are so-called complete metric space. Okay, so in order to do this, we have to show two things, right? We have to show that we have to let a complex convergent sequence be arbitrary and show that it's Cauchy. And then we have to let an arbitrary Cauchy sequence exist and then prove that it's convergent. Okay, so let's do this kind of step by step. So maybe we'll start with the easier end. Okay, so we're going to go ahead and let z sub n be a convergent complex sequence. Since it's convergent, that means we kind of know in advance what it converges to, or at least we can say that it converges. So we're going to also suppose that we'll just say Zn converges to Z in the complex numbers. Okay, and so we're also going to go ahead and let epsilon be arbitrary. And we'll let n be the natural number such that for any integer beyond that threshold, we have that the difference between z sub n and z is less than epsilon. Okay, so now we want to show that this thing is Cauchy. So we essentially want to note that for n and m bigger than that threshold, we want to show that the difference between z sub n and z sub m is less than epsilon. I can make that as small as I want. So we're going to do the same trick that we did in part A, right? We're going to shove a term in between the z sub n and the z sub m. Do you have any guesses on what that could be given what we already know? Well, we know that z sub n is convergent, which means that we know that it goes to the limit z. Okay, so what we're going to do is we're going to say that this is equal to z sub n minus z plus z, which doesn't really affect this at all, minus z sub m. Okay, and so at this point, we can kind of pull the same trick, right? We can group these together, we can group these together. I'm not going to go through the details again, but we're going to use the triangle inequality to show that this is less than or equal to z sub n minus z. plus, and I'm going to go ahead and flip this, z sub m minus z. Okay, and we know that since both of these are past the threshold, both of these are going to be less than epsilon over 2, and so we get that it's Cauchy, right? The difference between the nth and the mth term beyond some threshold is less than epsilon. So, and that proof works in any metric space. We really didn't do anything special there. Okay. So now what are we going to do? We're going to show the reverse direction. We're going to let z sub n be Cauchy and show that as a result it converges in the complex numbers. Okay, so let's see how that works. Okay, so the other direction, we're going to let z sub n be a Cauchy sequence of complex numbers. What are we trying to show? Well, I'm actually going to do a little bit of scratch work. So what we're going to show ultimately is we know that it's Cauchy, which means that for n and m beyond the threshold, we know that z sub n minus z sub m can be made as close as I want to each other. And somehow from that, I want to somehow show that as a result, the difference between z sub n and z is also going to be less than epsilon. So this should be a little suspicious, right? And it should be suspicious for the reason that we don't necessarily even know what the limit is. I made a big deal that for Cauchy sequences, you don't have to know what the limit is. So why do we kind of know what the limit is? Well, the idea is going to be for this Cauchy sequence, we're going to break it up into real and imaginary components. And the modulus of both of them are going to turn into sequences of real numbers. Okay, and since they're going to turn into sequences of real numbers, them being Cauchy immediately implies they're convergent, which means we know what they're going to converge to, or at least we can kind of specify. And we can go from there. So we're going to let z sub n equal x sub n plus I times y sub n, and likewise for z sub m. Okay, so everything I'm doing is like not a part of the proof. I'm just gonna like move this to the side. This is like scratch work, basically. This is to organize our thoughts. And we're just gonna mess around with this absolute value right here. Okay, so what we have is we're going to have x sub n plus I y sub n minus x sub m plus I y sub m. Okay, and that's going to equal what? Well, I'm going to kind of push the real terms over, and group the real terms, and I'm going to also group the imaginary terms together. Okay, and at this point, we have two complex numbers. Even though the thing I just put in parentheses is technically real, doesn't matter. All real numbers are complex. And we have this complex number, so by the triangle inequality, this is going to be less than or equal to xn minus xm plus I times yn minus ym. But remember, according to a property that we actually proved, the modulus of the product is really going to be the product of the moduli. And so this is really going to be equal to the absolute value of I times the absolute value of yn minus ym. And the modulus of I is just 1. I'll have you think about that for a second, maybe plot it on the unit circle, but the modulus of that is really 1. And this other term just kind of drops down. And that's now pretty interesting, right? Because now we have two essentially moduli of real numbers. Okay, and so I'm going to go ahead and maybe let's see, argue that this sum right here is clearly going to be bigger than or equal to just one of them, because these are both positive terms. So maybe I'll just include this one, for example. All right, and so as a consequence, what have we just showed? Well, we just showed that if I have something like this, with the complex numbers, I just showed that the difference between those two terms is always going to be bigger than or equal to this. And we also have something similar for the y sub n's and the y sub m's. Why is that significant? Well, we know a little something about these. We know that these are both less than epsilon. By the definition of Cauchy, we assumed that these were Cauchy, which means we have that these are less than epsilon. Well, since those are less than epsilon, that means that these are less than epsilon, which means we have essentially two real Cauchy sequences. And since we know that Cauchy sequences in the reals are automatically convergent, so in R, we immediately know that the sequence, which we can call xn, has to converge to something we'll call x, and we know that y sub n converges to something which we'll call y. And so from there, we're going to show that z sub n is going to converge to what? X plus iy. All of this was just the sketch of the proof, and now we can actually start to put things together. Okay, so I'm not going to really show all the nitty-gritty because we already did that, and it's easily verified. So let z sub n be a Cauchy sequence of complex numbers, and just as in all these proofs, let epsilon, that's the worst epsilon ever, be arbitrary. Okay. Then, and maybe we should probably define for z sub n equal to maybe x sub n plus I y sub n, and same for this. We have what? We have that z sub n minus z sub m is, let's see, less than epsilon by the definition of Cauchy. And we also have, from our scratch work, we also have that z sub n minus z sub m is bigger than or equal to both the real and the imaginary parts separately. So actually, I can really just combine this into one thing. So we really have, let me just zoom in here. So we really have x sub n minus x sub m less than or equal to z sub n minus z sub m less than epsilon. And the same thing for the y's, y sub n minus y sub m less than or equal to this. By the way, this is another exercise that we kind of just showed, that essentially the real part of any complex number is less than or equal to the modulus of the complex number itself. Likewise for the imaginary part. Okay, so this is another exercise that we kind of showed, but it's not a part of our proof. Okay, and so from here, what we have as a result, so therefore, we have that xn and yn are Cauchy sequences of real numbers, and thus we have that xn and yn are convergent. So we'll just go ahead and say that xn converges to x, y sub n converges to y. Since we know that they converge like that, we really want to show what? Well, we'd like to show ultimately that z sub n minus z, so let's let z just equal x plus iy, and we ultimately want to show that z sub n minus z, we want to show that that's less than epsilon. Okay, well, let's figure that out for a second. So we know that this is equal to x sub n plus iy sub n, and we know that z, by our definition, is x plus iy. So we're going to group the x's together and the y's together. we're going to bust out the triangle inequality. I didn't include the I component because the modulus of I is just 1. Okay, and since these are convergent, by the definition of convergent, that means that these are both going to be less than maybe epsilon over 2. Okay, and that's going to essentially equal epsilon. So I guess, technically we should say as a result, so I'll just kind of include this right here. So x sub n converging to x implies, and we already established the threshold, I think. Actually, no, we didn't. So we should probably specify that. So it implies that for any epsilon, there is an n such that for all terms beyond that threshold, we get that xn minus x is less than epsilon over 2. And the same thing for y sub n, so I'll just maybe do y sub n going to y, and then, very similarly, y sub n minus y is less than epsilon over 2. Okay, so I'll just kind of include that right there. And then after that, then we're allowed to go up here, okay? So that should be included to be absolutely rigorous, but hopefully you kind of get the idea, okay? So the structure of this proof is essentially piggybacking, and it requires you to know that the real numbers are complete. Otherwise, you wouldn't be able to do this. So the completeness of the complex numbers follows from the completeness of the real numbers, and I hope that was helpful.